So what I want to look at here is an alternative method for solving systems of equations. Now, this question here would have been the last question that I would have done in the last week's lesson. Okay, and let's just go back and take a look at how I solved that. Okay, so if we take a look at the general method that we use, so first of all, would I even have to do all this process if there was no parallel planes? Help me out here. If there was parallel planes, would I be going through this whole process? Okay, no, because, I could sort of judge, if there's two that are parallel and distinct, right away, there's no solution. Or if there's two that are coincident and the other one's not parallel, then I know there's a line of intersection, and then I solve it like the intersection of two planes. Okay, so this whole process assumes that we're starting with a scenario where there's no parallel planes. And the main way we solved these was to use elimination. So here I eliminated x using equations 1 and 2, but then I also eliminated x using equations 1 and 3. And that left me with 2 equations and 2 unknowns, which I could solve as usual. But when you look at these examples, you realize, well, what am I allowed to do? I'm allowed to multiply both sides of the equation by some number. Okay, now what's the only thing that actually changes if I multiply, say, equation 2 by 3? What's the only thing that actually changes? So if I multiply these two sides of the equation by 3, I notice that the only thing that changes are the coefficients to the variables. Okay, the variables themselves don't change. It's still that same x, y, and z, which, if we're thinking geometrically, represents a point on the plane that's on all 3 of these planes, that point of intersection, or one of the points of intersection. Okay, so when you're multiplying both sides of an equation, you're just affecting the coefficients. When I'm adding or subtracting 2 equations, what's the only thing I'm affecting is the coefficients, because I keep adding like terms. So the variables never actually change. Okay, so at some point, somebody had the bright idea and said, well, you know what? Instead of having to rewrite all these equations every time, if the only thing I'm working with are the coefficients, why don't I just write the coefficients? Okay. Now, I just want to remind everybody that this is like a very, very brief introduction into a mathematical representation that is useful way beyond just solving systems of equations. Okay, so what I'm going to be presenting here, okay, can be used in other representations. All right. So let's take a look at what we're going to do. So the idea here is, if I'm just going to work with the coefficients, is I set up what's called a matrix. Okay, so a matrix is just an array that contains rows and columns. And in this case here, it's going to have 3 rows, so 1 for each of the equations, and it's going to have 4 columns. Okay, but I'm going to separate them out because I'm going to have 1 column for the coefficients of x, y, and z, and then that 4th column, which I'm going to separate out by a dotted line, is going to be what that linear combination is equal to. So one of the things you'll notice here is that I'm representing this linear equation, which of course we know represents a plane in 3D, okay, with the constant value on the other side of the equation. Okay, and what we use, and there's, similar to vectors, I could use round brackets here, I could use square brackets. I'm just going to go with what the textbook uses. They use square brackets. And instead of writing out the whole equation, I'm just going to write out the coefficients. So 1, -3, -2 equals -9. I'm going to leave myself a little bit more room there, because we're going to separate that out by this dotted line as a reminder that that fourth number actually lives on the other side of the equation. Okay, and then we have 2, -5, 1, and then 3, and -3, 6, 2, 8. Okay, and this matrix represents this system of equations. All right? So instead of manipulating equations, we talk about manipulating rows. All right? So for those who are just coming in, I'm just talking about how when I was solving a system of 3 equations and 3 unknowns, when I multiply the equation on both sides by some number, or I add and subtract 2 equations, it's only the coefficients that change. The variables don't, okay? Because multiplying a monomial by some constant doesn't do anything to the variable. Adding and subtracting equations is just involving adding and subtracting like terms, which doesn't change the variable. So like I said, this matrix here is a representation of that system of equations, okay? But remember, keep in mind that this is not the only scenario with which matrices are useful, and these operations that I'm showing you are useful. So instead of operating on equations, we're now going to operate on rows, okay? So these are what we call the elementary row operations, okay? So let's see what's legal. Well, what's legal is what was legal before, okay? So we can multiply both sides of an equation by some constant, okay? And we can add and subtract equations to create new equations, okay? So here I did 2 times equation 1 minus equation 2, and that created a new equation for which y and z still represents the y component and z component of a point of intersection, okay? So I'm going to do the same thing here, except instead of multiplying the equation, I'm multiplying the row. So if I wanted to multiply this row by 2, each of the terms would be multiplied by 2, exactly like I would be doing when I'm doing it with an equation, okay? Instead of adding and subtracting equations, I'm going to be adding and subtracting rows. Now, not surprisingly, the goal is still to eliminate terms, except here, when I'm eliminating, say I'm trying to eliminate the x, I'm just eliminating the coefficient. I want to turn this coefficient to 0, okay? But when I add 2 equations or subtract 2 equations together, I'm going to come up with another equation, a new equation, okay? I don't want this matrix to keep growing bigger and bigger and bigger where I start adding more rows. So what we do is once we add equations together, it's going to replace one of the rows in my matrix, okay? There's actually one more elementary row operation, but I'll talk about it when we need to use it, okay? So again, what you have to, and I'll tell you right off the bat, that solving this using matrices for 3 equations and 3 unknowns is not necessarily faster, okay? But if you start to get to 4 equations and 4 unknowns, 5 equations and 5 unknowns, this is a much more efficient way of doing it, okay? So what this is doing is it's just introducing you to the idea of working with a matrix, okay? And if you take linear algebra next year, well, you'll start to see all the other uses that matrices are good for. Okay, so as before, I want to make sure that I'm identifying the operations that I'm performing. Okay, this is where things are different, and I'm very happy about this system of equations because I'm very happy about having a 1 as my first element in my matrix, which represents the coefficient of x. Because what I'm going to do is I'm going to use this to eliminate x with the other 2 equations. So it's like working with equations 1 and 2, and then equations 1 and 3. In fact, exactly like what I did in this here, okay? I multiplied this by 2 in order to eliminate the 2x here. Multiplied this by 3 in order to eliminate the negative 3x there. So we're going to do the same thing, except with these rows, okay? I'm just going to, there we go. That's a little clearer. Okay. There's one little thing, though, that I'm going to make a suggestion on. The textbook doesn't do this, you know, and it's not that they're wrong. It's just, like I said, sometimes I try to give you tips to try to avoid mistakes. And instead of subtracting rows, I'm going to say that we're always going to add rows, because if I have to subtract the -5, I have to remember, oh, minus -5, I'm adding -5, okay? Whereas if I'm always adding rows together, okay, here adding 2 is just plus 2, adding -5 is just subtracting 5. You don't have to think about it. So instead of multiplying this by 2 in order to get a 0 here when I combine these two equations, guess what I'm going to multiply this by? So who's going to tell me what I'm going to multiply it by so I can use an addition instead of a subtraction? So I need to change this row so I have something that's going to help me eliminate. There you go. Well, if I do -1, then -1 plus 2 doesn't give me 0. And remember, I want to eliminate the variable. So you're close. I'm not going to multiply this row by -1. Yeah, there we go, -2. I figured that's what you meant. So what I'm going to do is I'm going to do -2 times row 1, and I'm going to add row 2 to that. And then that's going to create the elimination of the x coefficient. But remember what we said is I don't want to start adding rows to my matrix. So whatever new equation I get is going to replace R2. So that's what this represents. Okay, I'm going to multiply -2 times R1, add R2. That's going to create some new equation, and that's now going to replace my second row. Okay, so my first row doesn't change. Okay, so now let's do it. -2 plus 2, 0. Exactly what I wanted. -2 times -3. So 6 minus 5, 1. Okay, that's going to be 4 plus 1, 5. And then here, 18 plus 3, 21. Okay. Now, if you look back to the one we solved the other day, you're going to see that the equation we got was, y plus 5 equals 21, or maybe it was -y minus 5 equals -21, but essentially the same equation. But I'm going to want to do this a second time to eliminate the x twice. So I'm actually going to do it in the same operation. I'm going to use this one here to help me eliminate the x coefficient in that one. So now I'm going to do 3R1 plus R3 and replace R3. Okay, so just to give you a tip, you don't want to do two operations that are manipulating. So I don't want to change R2, but then also use R2 to change R3. That I don't want to do. I want to avoid that. But here, I'm not changing R1. I'm not changing the first row at all. So it's okay to use it in two different operations. So let's do it here. So 3 minus 3, 0. Okay, -9 plus 6, -3. Okay, here -6 plus 2, -4. And if you can make sure you're checking my algebra here. So this is -27 plus 8. -27 plus 8 is -19. Okay, so essentially, this is like creating two equations and two unknowns because this first coefficient is equal to 0. So now I'm going to work with this system of equations, just the last two rows, to eliminate one of the other variables. Can anybody guess which variable I'm going to eliminate? There you go. I'm going to use the fact that this represents y that I'm going to use to eliminate this -3. Okay, so let's just do it, and then I'll talk a little more about it. So now what do I have to do? I have to do, well, 3 times row 2. And I'm going to add that to row 3. Remember, I always do additions. And then I'm going to use the new equation to replace row 3. So let's see what happens. I'm not changing first row. I'm not changing the second row. But now this is going to be, let's take a look, 3 minus 3, 0. Obviously, 3 times 0 plus 0, that still stays 0. Okay. Then we've got 15 minus 4, sorry, where am I? 3 times, yeah, 15 minus 4 is 11. And then here we have 3 times 21, 63 minus 19, 63, 53, 43, 44. Okay. And essentially, this is my goal when I'm solving a system of equations using matrices, is I'm trying to get this triangle of zeros here at the bottom left corner. So this is why when you're working with matrices, you're always going to follow the same process. I'm always going to try to get a 1 in this position, start by eliminating these two coefficients, and then once I have these two zeros here, I can use this row to eliminate that coefficient. Now here it was very nice because I had a 1. But even if I had a 2, I could just multiply both rows. Okay, I could have just done, say this was 2, I could have done 3 times R2 plus 2 times R3. I would have still been able to eliminate that there. So your goal is to get this triangle of zeros in the bottom left. Okay, because now what does this last equation tell me? If I think of this as an equation, what's it telling me here?
That z equals 4.
There you go. I'll even take one step back before then. I'm going to say that it tells me that 11z is equal to 44, which then of course means z is equal to 4. Okay? Then I can take this and go back to the previous equation. Y plus 5 times z is equal to 21. So y is equal to 21 minus 21. And then lastly, I can take these two and put it into the first equation. X minus 3 times 1 minus 2 times 4 is equal to negative 9. So x is equal to, so negative 3 minus 8 is negative 11. Bring that to the other side, plus 11. X is equal to 2. And there's your solution, which is the one we got before. Okay? So this is what we call bringing it down to row echelon form. Okay, the idea echelon is like a, I don't know if you speak French, you know that échelle means ladder. So it's kind of like creating this ladder here, this triangle of zeros. So row echelon form. And this is often not where we stop, especially when you're using this idea of row operations in a linear algebra course. This is actually not the format you want to stop at. You want to actually keep going and now use this number. So first I would divide by 11, to get 1 and 4. Okay, and then I would use this to eliminate those two positions. Then I would use row 2 to eliminate that position, and I'd get a triangle of zeros both at the top and at the bottom. So the only numbers that are left are in this diagonal. Okay, if you're interested in seeing that, I'm going to post up 2 other examples. Okay, and one of those examples is going to show me bringing it all the way down to what we call row reduced echelon form. That's the one that's particularly important in linear algebra. Okay, but it's just following the same steps. So if you're interested, you can go take a look. So when you take a look at the work that I did here, and you take a look at what I did last time, well, it's not really looking like you're saving much time. Okay, but remember, what this is doing is it's just introducing you to this idea of working with these row operations. All right. Any questions we want to ask before I quickly do one more example, just to kind of show you something else? All right. So I'm going to do the same thing here. Okay. And I chose this one because we're going to see it's a slightly different scenario that's going to come up. But is there something you see that's not particularly ideal based on what I talked about in this first example? What did I say I would ideally like to start with if I'm going to follow the exact same algorithm every time? What would I like to have here that I don't have that I had in this first It has to do with this first step.
We don't have a y value in the first equation.
Yeah, well, I'm not too worried about that, actually. You are correct, but I'm not worried about it. There's something else that I like less, though, than that. Remember we said it would be really convenient to have this leading 1 here at the top right? Because then I could use it to easily eliminate the other 2 positions. That's not what I would have here. But this is where we come to the third elementary row operation. Does it make any difference if I write these in a different order? Does it change the solution to the system of equations?
No.
Exactly. And that's the third elementary row operation. So we've got multiplying a row by a constant, adding and subtracting 2 rows and replacing one of the rows. And the third one is interchanging rows. Not something that's particularly useful when we're solving a system of equations the other way. You don't need it because you just start with whatever's convenient. If it's more convenient to work with 2 and 3 first, you do that. Whereas when you're working with matrices, you really want to focus on having the 1 at the top. So the first thing I'm going to do when I'm writing out my matrix is I'm going to interchange these 2 rows. I'm going to put this one first, 1, negative 1, negative 1, negative 4. Then I'll put, no, it doesn't really matter here, I'll put this one here, 2, 0, because there's no y, negative 1, 3, and then 1, negative 7, negative 4, negative 37. And this is what I'm going to start with, okay? And sometimes it's even convenient to interchange 2 rows in the middle of the process. That's perfectly fine. It's a legal operation. Okay, so I'm looking at the time, so let's maybe do this kind of quickly. Okay, but again, I'm following an algorithm. I'm always doing the same thing at first. I'm taking this 1 here and I'm using it to eliminate those 2. So what am I going to do? I'm going to do negative 2 times row 1 plus row 2. That's going to help me eliminate the 2 there. And I'm going to replace row 2. And then I'm going to do the same thing with row 3. I'm going to do negative row 1 plus row 3. And I'm going to replace row 3. Okay, so keep an eye on my algebra, please. Negative 2 plus 2. Well, actually, let me write row 1 just so that it's done and out of the way. So negative 2 plus 2, 0. 2 plus 0 is 2. Okay, negative 2 times negative 1, so 2 minus 1 is 1. And then here, 8 plus 3 is 11. Okay, so let's go to the next one here. So negative 1 plus 1 is 0. 1 minus 7 is negative 6. And then here we have 1 minus 4 is negative 3. Okay, and then here we have 4 minus 37. 4 minus 37 is negative 33. Okay, so now let me do the next step. Now that I have these 2 zeros here, let's get my 0 there. Okay, so let's see what happens. I guess I'm going to do 3 times row 2 plus row 3, and I'll replace row 3. Okay, and so first row doesn't change. Second row doesn't change. And the third row, so obviously 0 plus 0 is still 0. Here we have 6 minus 6, 0. Here we have 3 minus 3, 0. 33 minus 33, 0. What does that mean? What does row 3 tell me? I'm not sure that it tells me that, because row 3 seems to tell me 0x plus 0y plus 0z, which is 0, is equal to 0. When is 0 equal to 0?
Always.
Always. So remember that when we get something that's a true statement, the implication is, yeah, that there's infinitely many solutions. What do you think we would have seen if it meant there was no solutions?
A contradiction.
Yeah, I probably would have had 0, 0, 0, 7. And then I would have had that 0 is equal to 7. And then that would have told me that there was no solutions. Okay. And by the way, you can make geometric interpretations of this because, you know, so in this case here, the three planes are not parallel and I have infinitely many solutions. So what's the geometric interpretation if there's infinitely many solutions but none of them are parallel?
They intersect in a line.
Must intersect in a line. So it has infinitely many solutions. That's great. But what I would like is even better is to know what those solutions are. But this is where now, like we did in the past, we're just going to now work with the remaining two equations. So if I take row 2 tells me that 2y plus z is equal to 11. And guess what I'm going to do now? I'm going to do what I did before, is I'm going to write one of the variables in terms of the other. And then I'm going to take this information and put it into the first equation to write the other variable in terms of, again, might as well use y. So x minus y, and then wherever I see z, I'm going to replace that by minus 2y plus 11 is equal to, what is it, negative 4. And now I'm going to write x in terms of y. So x negative plus 2, so this is going to be plus y minus 11 equals negative 4. So x is equal to negative y plus 7. And so like before, I'll let y equal t, and the solution to my system of equations is going to be x equals negative t plus 7, y equals t, and z equals negative 2t plus 11, where t is all real numbers. Okay? So as before, just because we're using a new setup, the algebra takes me to where I need to go. So in this case here, the first place the algebra took me was that this row of zeros implied that there was infinitely many solutions. Then I could use the work I had done to write my equation of a line. Okay? So this is, the briefest of introductions to solving systems of equations using matrices. Okay. Now, like I said, with a 3 by 3, 3 equations, 3 unknowns, probably not faster than what we did before. But once you start to get to 4 equations, 4 unknowns, 5 equations, 5 unknowns, this is a much more efficient way of doing it. By the way, who else do you think would like doing things this way? In this nice algorithm, always the same step every time. Who else do you think likes this? Who do you know that really likes things that are algorithmic? There you go. Your computer loves that. Well, Tony loves all math, so it's tough to really say whether I love this more than the other way. But definitely the computer prefers this. Okay? So when you look at solving large systems of equations online, guess what you're going to find? You're almost always going to find something that uses matrix representations to do the solutions or to even give you the solutions. Okay? So like I said, for the assignment, you do not need to solve things using matrices, but if you want to, as a way to practice, not a bad idea. Okay? And if you're writing the final exam, again, there's no question that's going to say you must solve this using a matrix. All right? So that's the end for now. Any questions? Okay, so I will be posting, so this will be called part 1 of the lesson. I will be posting a part 2 that's just going to have 2 other examples. And in one of the examples where there's a single solution, you're going to see me not stop at row echelon form. I'm actually going to keep going and solve it all the way to what we call row reduced echelon form, where you're going to have the triangle of zeros. Okay.